Let me just present. Okay, so girls, I want to, oh, Armida asked me a question about the, I'll post the recording when it's done, okay? I didn't post it last time because I'll be honest with you, I wasn't happy with it. I don't think I explained anything very well in that, well, there's a couple of things I thought of it, listened to it again. I'm like, you know what? I need to do a better job of explaining what we just talked about. So I actually want to kind of do like a redo. And I went through the PowerPoint and I made it simpler, more direct, more efficient. So I want to go over static electricity and try to make it a clearer picture of what it is, okay? So last time we talked about electricity, but I want to kind of redo it. So electricity, we said last time, is the flow of charged particles like electrons, right? And there, we talked about two types, static and current electricity. So I want to actually show you the difference. So I think it may be better to actually show you what this looks like. So let me pull that up, okay? So this is current electricity, okay? So what's happening in current electricity is you can see the electrons are just moving around constantly, like current in a river. This is current electricity, okay? This is what we're going to talk about next week. Static electricity is when the charges don't move, they accumulate, because the word static means they're stationary. So for example, if I take a balloon, and it's actually one of the simulations you're going to be doing, and I rub it on the sweater, you'll notice that the balloon has picked up the extra electrons, and it looks like the sweater has lost the electrons, right? But you notice that the charges aren't moving. They're just stationary. They're static, all right? Now, if I let the balloon go, you'll notice that it gets attracted to the sweater. And that's because, we talked about this last time, opposites attract, right? So this is static electricity. You see the charges are not moving. They're static. That's what static means, not moving. Now, eventually what happens over time is that the balloon will lose those electrons and the sweater does gain those electrons. But we'll talk a little bit about that later on, okay? So that's the difference between static electricity and current electricity. Static, their charges are held, okay? Any questions about that? So static cling is like, you know, when you take a, like for example, the balloon is, I guess you could say it's, you know, that is exact example, sorry, of static cling is the balloon and the sweater. You've all experienced that, like last time I mentioned that you take a sweater off and you can feel the static energy, things that will, you know, attach to other things. The reason why they're attached to them is because they have a difference of charge, kind of like what you're seeing in this picture. Okay. So as you saw in the animation, the way you build the charge is actually through friction. Okay, if I go back to the animation and I reset it, you can see that if I take this balloon and I rub it through friction, what happens is the balloon picks up, in this case, the electrons, and the sweater loses the electrons, right? So building the charge requires two different types of insulators. Now, I need to explain why it has to be insulators, and I realized I did not do a good job of this last time. So let me explain what that means in a minute, okay? Why does it have to be two insulators? Why not two conductors? Because the balloon is not made of metal, and the sweater is not made of metal. These are not conducting materials. These are insulators. So why do they have to be insulators to do something like this? Like, in other words, if this balloon were made of aluminum foil and I did this, nothing would happen. It wouldn't work. Why does it have to be insulators? So a conductor is different than an insulator. A conductor is something that will allow charges to move through it really easily. That's why we make wires out of conductors. But insulators don't allow charge to move easily through them. And I mentioned this time, this is why you put the insulator around the wire so that when you touch the wire, you don't get an electrical shock, right? Conductors we know are made of things like metals. Remember, that's one of the physical properties of a metal is being a conductor. Insulators are non-metals. Things like glass, wood, plastic, that you're seeing in this image here, okay? So why does it have to be insulators? Why can't we build the charge with the conductors? So let me do a better job of explaining this because wasn't happy with the way I explained it. So here's the thing. As you saw in the animation, I can take two insulators, I can rub them against each other, and you can see one will pick up the charge, the electrons, the other one loses them, and that's static electricity, right? So that's what you're doing when you're building the charge. You take something like A. So imagine A is one of your insulators, and B is another insulator. You rub them against each other through friction. Now what happens is the friction heats things up, and we know that from particle theory, when particles get heated, they move faster. What happens is they gain enough energy to transfer, to move from one substance to the other substance. In this case, as you saw with the animation, the electrons move from the sweater to the balloon. Okay? Then when you separate them, you can see that the charges are held in place. There's your static electricity, right? Now, why can't we do this with conductors? Because conductors allow electrons to move really easily through them. Imagine that A and B were two metals and we rub them against each other. Now, let's imagine hypothetically that, let's say metal A picks up an electron from B. Now, what happens then is metal A becomes negatively charged. Well, as soon as it becomes negatively charged, because the electrons can move really easily through a conductor, those electrons are going to move back into substance B, which was positively charged. So the conductors, because the electrons can move so easily through them, as soon as they pick up an electron, they're going to get rid of it. And insulators don't do that. They'll hold on to the charge, okay? Any questions then why it needs to be an insulator to build a static charge through friction? Okay, so again, the idea is if the balloon and the sweater were made of metal, as soon as the balloon picked up an electron, it would automatically give it back to the sweater, because conductors don't hold electrons very well. I hope that's a better explanation. Now, what happens over time is, so if I build my charge, right now it looks like nothing is happening, right? Well, eventually what will happen is the balloon will become neutral again, and the sweater will also become neutral again. So over time, slowly, the balloon will lose electrons to the air, and the sweater will gain electrons from the air. Slowly. That will happen really, really slowly, okay? Or it can happen really, really fast. So here's one. It's called John Travoltage. I don't know if you guys know who John Travolta is, okay? Like, he's an older movie star. I'm pretty sure you know him from Grease. Probably you know him from Grease. But anyways, so here's the deal. Look, if I take John Travolta, and you can see he rubs his foot on the carpet. So what happens is, you can see when he rubs his foot on the carpet, he picks up a charge. He picks up the electrons from the carpet. But because he's near the doorknob, what happens if I move him really far away? Watch what happens. Okay, so right now he picks up the charge. Okay, so he's negatively charged, but he's too far from the doorknob, right? So what happens then is when he gets close enough to the doorknob, discharge. Okay. So a discharge is when an insulator will quickly become neutral again by generating a spark, something that you could see, you can feel, you can maybe hear. Okay. And then what happens is after that spark, you'll notice there's no more spark, right? It disappears. The only way you get a second spark is by recharging. So you can generate multiple sparks, but every time you generate a new spark, before you do that, you have to recharge. So this is like for example, for lightning. Lightning is exactly the same thing. In lightning, what happens is you have a cloud picks up a charge, and then eventually there's a lightning bolt. But you know from there's a storm that was it a couple of days ago, constant lightning, because you know once the discharge happens, there's more recharging that happens, right? And which then causes another lightning strike, and then there's more recharging, which causes another lightning strike. So it's really no different. Lightning and this is exactly the same mechanism. Okay, and that's what you're seeing. So you can see in this picture here, right? So lightning is this kind of the same idea as what you saw with the animation. Like, how does lightning form? We're just going to talk about that later on, but I might as well just address it now. Well, in the animation, you saw the person rubbing their foot on the carpet. Same thing happens in lightning. The hypothesis is that you have particles that are rubbing past each other, that are insulators, and they build a charge. And it seems like the negative charge accumulates in the bottom. And what happens then is it creates a lightning bolt, which that's going to be your discharge. That's going to be your spark. And then to get another lightning bolt, you just need to recharge the system, right? But how it actually happens, there's a little bit more I need to add to this so we clearly understand why is it that there is a lightning strike? Because the ground, why is the ground positively charged and why is the doorknob accepting that charge? There's actually something a little more to it than just what I'm mentioning it. So I'm gonna address that in a minute, okay? So we know that things that are the same charge repel, right? So opposites attract, like charges repel. And you can see that, for example, in this animation. And that explains the static cling, right? That explains why the balloon is stuck to the sweater. All right. This is an important concept in understanding electricity. It also helps to understand, for example, why is it that we see people's hair stand up when they're statically charged. So if someone is statically charged, now obviously they would need to build a pretty strong charge for them to see this effect. But I'm sure you've seen maybe those video clips when the person's touching, it's a type of generator and their hair stands up. So what's happening? Well, if I go back to the idea of this animation, we know that when someone is getting statically charged, you can see that they're not neutral, right? So in this case, it's showing that John Travoltage is negatively charged, right? Now, what happens? Oh, the animation's making a lot of noise. Let me mute it. I can't mute it. Okay, let me just discharge it. Making a lot of noise. I don't know if you can hear the noise, but it's like killing my ears. So as you saw, when John Travoltage picked up that charge, he was negatively charged, right? Now, what does that mean? Well, that means that even his hair follicles would be charged. So for example, if if each hair strand is also negatively charged, then it explains why hair stands up, right? And that's because, normally the hair follicles are like right beside each other when neutral. Okay, that's fine. You comb your hair, whatever. But if they're charged, they're going to want to be as far apart from each other as possible. That explains why the hair stands up. So we can use the law of attraction and repulsion to explain, why is it that your hair stands up. But we can also use this law to explain what happens in the discharge. Okay, which I'm gonna, so in other words, if you're seeing in this picture here, in the bottom, on this picture and in this picture, there's that discharge. We can actually explain that using the law of attraction and repulsion also. So let me delve into that. Okay, let me explain that. So if I go back to the animation with the balloon, you'll notice something really interesting when I move this balloon towards the wall. You'll notice, now, so the balloon is negatively charged, right? You can see that as I move it towards the wall, the electrons get pushed away from the balloon, right? Now, why are they doing that? Why are they getting pushed away from the balloon? It's interesting. Why are they getting, well, because that's the law of attraction and repulsion, right? The balloon is negatively charged. So as the balloon approaches the wall, if the electrons can move, then they're going to want to move away from the balloon. You can see that. Okay. This, by the way, there's a term for this. It's called induction. We will talk about this in a few moments. Okay. And you can clearly see what's going on. That's called induction. So that actually explains then what's happening here in this image. You can see that the ground has become positively charged. For some reason my pen's not working here. Okay, you can see that the ground has become positively charged, and that's because the bottom of the cloud is negative. So those electrons in the ground, they get pushed further down, which makes the surface positive. Now what you have is you have an imbalance of charge, right? You have a negative charge here, and now you have basically a positive charge there. So for a discharge to happen, you need this setup. You need one side to be negative and one side to be positive. And then you'll get a discharge. You'll get that lightning bolt, or you'll get that spark. So in that animation with John Travoltage, what's happening is as his hand is approaching the doorknob actually becomes, the surface of the doorknob becomes positively charged. So that makes, hold on, let's move this. So if that's his finger, and if he's negatively charged, and here's the doorknob, and the doorknob, we know doorknob is made out of metal. So what happens is the electrons are going to move away. They're going to want to move this way, which means the surface of the doorknob becomes positive. This, by the way, is called induction. Okay, it's called induction. Then what happens is when you get close enough, the electrons are going to jump across, and that's your discharge, which produces a spark. Okay. Okay. All right. Now, we've been looking at one way to charge an object, which is through friction. There's a term for that, and that term is called tribal electrification. Okay, so what we've been looking at, taking the balloon and rubbing it against the sweater, that's tribal electrification, right? you know, for example, taking a comb, going through your hair, that's basically tribal electrification, charging by friction. For the example, in the top right corner, you can see that there's a plastic rod and a cloth. Those are both examples of insulators. I can see that initially they're neutral, but after the cloth and the rod have been, you know, rubbed past each other and you have friction, you can see that the rod has lost electrons because the rod has become positively charged. So the cloth obviously picked up those electrons and become negatively charged, right? That's tribal electrification. Now, that's one way to charge. There are two other ways to charge. One is, oh, I should mention this before I move on to the other two ways. How do you actually know what becomes positive or negative? This is actually one of the questions I think you have to do in your CPT. So there's actually a useful chart to help us know what becomes positive and negative. So for example, here, where is it? Not there. Here, this is showing that the glass rod, sorry, the plastic rod became positive and the cloth became negative. How do I know that? So there is a, sorry, where's that chart now? There's a chart here that actually allows us to figure this out. It's called the tribal electric series. Basically, if I have two materials, the chart tells me which one becomes positive and which one becomes negative. So for example, if I take wool and polyester, so wool is here, okay, and polyester is down here. So it says that polyester wants to be negative and wool wants to be positive. So if I rub wool and polyester together, what's going to happen is the wool will become positive and the polyester will become negative according to this chart. Otherwise, I'm not going to know. So if I, for example, take vinyl and glass, vinyl is down here and glass is up here. So glass will be positive, vinyl will be negative. Okay, so this allows me to determine what will become positive and what will become negative. You'll notice that the metals kind of like in the middle because they're conductors, right? So they're not going to be able to pick up charge through friction. Okay. The other way to charge something is through something called conduction. Now, in conduction, what happens is you have an object that is charged. Okay, so you can see it right here, an object that has a charge that makes contact. So in conduction, you have to have contact. Okay, makes contact with another object, and the charge can freely move into the next object. Okay, but they can freely move because they're making contact because they're touching. So that's conduction. All right. You'll notice here we have this thing. It's called an electroscope. An electroscope is a device that allows you to determine if something is charged. So what happens in the electroscope is you see these are leaves, metal leaves. Now, if the object is not charged, the metal leaves are just going to hang like this. They basically are parallel to each other. But what happens when they're charged is they move apart. And you can see that here. And again, that's the law of attraction and repulsion, right? So if I take an object that's positively charged and I move it towards my electroscope, the electrons are going to move up because they're attracted to the positive charge. That means the top of my electroscope will be negative and the bottom will be positive. And because these two leaves are the exact same charge, it's kind of like what happens with, no, not kind of, it is exactly what happens with the hair standing on your head. Because they're the same charge, they're going to want to repel and move apart. You can see that because the rod is positively charged, when it makes contact with the electroscope, you'll notice that there's less positive charge now, and it's because electrons went into the rod. So this picked up some electrons from the electroscope. So this is charging by conduction, by contact. Okay. So that's a second way to charge an object. We have friction, tribal electrification, or we can charge things by contact or by induction. So this one might be a little bit trickier to understand, but I think with the animation, kind of makes a lot of sense. So number induction is when you take an object that's charged and you move it towards another object, and the electrons, well, in this case, the electrons get pushed away because the balloon is negatively charged. Of course, if the balloon were positively charged, then the electrons would be pulled towards it, right? And that's induction. So what happens in induction is something like this. Imagine you have two metal spheres that are, you see they're making contact, okay? Now, the bottom of the metal sphere, these are insulating materials, and we know insulators do not allow charges to move through them easily, okay? So what happens is you have two metal spheres that are both neutral, so they're not charged. You take an object that's charged. So in this case, you can see an object that's positively charged being brought towards the metal spheres, right? Now, what happens is induction. The object's positively charged, so the electrons are going to move to the left because they're attracted to this positively charged object. So the left side, you can see over here, this is negative. If I look at this, this is negative, which means this side will be positive because the electrons went to the left. Okay? This is induction. This is no different than what's happening here when I move that balloon towards the wall. It's the same thing. Okay? Now, if I then move the metal spheres apart, because the charge is imbalanced, because the sphere on the left has an accumulation of negative charge, and the sphere on the right, which is called B, has less negative charge, so it's positively charged. When I separate them, then what happens is they're charged. Okay? And that's, you can see, not through contact. So there's no contact between the charged object. You can see in the animation, there's no contact between the charged object and the metal spheres. This is induction, okay? Induction causes the electrons to move to the left, and then when you separate the spheres, we've actually charged them, okay? So that is charging by induction. That's the idea. You can see the same thing happening over here. So here is, in this case, a negative charged object. Now you notice that it's not making contact, so there's a gap. Again, so here's my electroscope. Here's the idea. The electrons are going to move, this is negatively charged, so they're going to want to move away, right? So the top of the electroscope becomes positive, the bottom becomes negative. So because both of the leaves are negative, they move apart. You can see that there. Now, if I touch the bottom, what happens is because this bottom has a lot of electrons, the electrons are going to want to move into the hand. Right? They're going to try to get away from the negative, I guess it's a balloon in this case. And then when I pull the hand away and then remove the charged object, because think about what happened to the electroscope now, right? The electroscope has lost electrons because when I touched it, I picked up electrons. So when I remove my hand and I remove the balloon, now my electroscope has become overall positively charged. So that's another example of charging through induction, okay? So that's a third way to charge an object. Any questions about the difference? So tribal electrification is rubbing two insulators. Conduction is by touching. I should mention a conductor. So what I'm charging has to be metal. So I'm making physical contact with a metal object, and I'm touching it with something that's charged. That's conduction. And then you have induction, where you're charging something without actually touching it. Okay, those are the three ways of charging objects. So in the beginning, there was an image of a cat. So let me explain then how this cat got styrofoam stuck on it. Basically, the idea is this. The cat is like John Travolta, walking across the carpet. So when you walk across the carpet, you build up a charge like we saw here. Walk across the carpet, you build up a charge. Now, what happens is if the cat doesn't discharge and it accumulates the charge, now the cat doesn't discharge, so it doesn't touch anything that's metallic, then the styrofoam would be attracted to it because it's actually the same thing that's happening here. So right now, if I take imagine the balloon is the cat, and the cat's walking across carpet, and it picks up a charge, and imagine the walls of the styrofoam. Now what happens is, because of induction, the balloon will stick to the wall like the cat will stick to the styrofoam, or we could say the styrofoam sticks to the cat. It's actually the same process. So what's happening then is the cat is charging itself through tribal electrification, and then through induction, the styrofoam sticks to the cat. One last thing I want to mention about discharging, just in terms of a safety aspect. I think I may have mentioned this. When something is charged, obviously there is a risk of electrical shock when there is a discharge. For example, when lightning. That's why you should be careful when there's a lightning storm. So then you can see here, it says to discharge. We mentioned this last time. When you come out of a car, you're sliding past the seat. It's kind of like rubbing your feet against the carpet. You pick up a charge, and if you touch something metallic while you're pumping fuel, I guess that theoretically could ignite the fuel and cause a fire. So the idea is to discharge, touch something metallic, like you saw in the animation, touch a doorknob or your car, which is made out of metal, so that when you do discharge, you're neutral and therefore you're okay. Now, in terms of electrical equipment, often electric equipment has things called grounding in it. And the idea behind grounding is that if you have an electrical appliance, let's say it didn't have grounding, then if it for some reason picked up a charge, let's say the appliance picked up a charge and became, whatever, positive or negative, and you approached it, well, what happened is, if it's a metal appliance and you got close, you would get a pretty nasty electrical shock, right? But grounding is a safety feature. So what happens in grounding is the appliance, well, if you think of the term, is literally connected somehow to the earth. So why is that important? Well, because if the appliance picks up a charge, for example, let's say it picks up a positive charge, right? Then what would happen is electrons would come in from the earth to make this neutral again. Or if this thing was negatively charged, then the electrons would move into the earth to make it neutral again. So Grounding is making things neutral by connecting them to the earth. So when there is a buildup of charge, the charge can move into the earth, that excess charge. You know, this is how lightning rods work, by the way. Okay. Or you could just let it sit, but that would take a long time, right? Letting it sit would take a very, very long time, but that would also work too. And we talked about lightning. So now you know what lightning is, right? Lightning is basically the cloud builds up a charge through friction, tribal electrification. The bottom of the cloud becomes negative. The surface of the ground, there's your induction, right? Because the electrons get pushed down. Eventually, when that difference is great enough, you will get a lightning strike. Okay. And by the way, can lightning strike in the same place? You know, there's a saying, say lightning can't strike twice, something like that. That's not true. Lightning can strike in the same place twice. That's a myth, by the way. Lightning doesn't care where it goes. Okay, why don't we stop there? And let me see, I'm going to stop recording. We'll call it quits.